Right next we have Gage Martin telling us about annular lengths, double branch covers, and annular Khovanov homology.
Thank you. Before I get started, I wanted to just thank the organizers of the conference for the chance to be here and speak with you all. And I also wanted to take a second just to say that we're all meeting on the ancestral and territorial, traditional territories of the Seminole and Miskosukee tribes, and I just feel like it's important to take a little bit of time to acknowledge that and reflect on it as a small part of thinking about the history, ongoing legacy of colonialism and genocide here in the United States. With that being said, maybe I'll tell you about some math now. And I should say part of what I'm going to be talking about today is joint work with Fraser Binns. And Fraser is a grad student at BC, and he's currently on the job market. If you or anyone who knows hiring postdocs in low-dimensional topology. And so I guess maybe a good starting point for my talk would be I could just define each of these three things a little bit for you, tell you about how they connect and like why I might care about thinking about them. And I'll just kind of go in order. So an annular link, like here is a true definition, but maybe not. That in light lane is just we're embedding our link into a thickened annulus. So instead of a link in S3, we're just embedding our circles into an annulus. And sometimes it's instead, like maybe you only really like to think about links in S3. There's an alternative definition, which like sometimes is more useful to think about too, which is we can think about it as just a link in S3 where we have a distinguished unknotted component. And of course, going between these definitions is just the fact that the complement of this unknot in S3 would be a thickened annulus. And I have drawn some pictures because I think those are kind of nicer than just writing down that a link is embedding inside of a thickened annulus. So here's three different pictures of annular links. And each time I've just kind of marked where the center of the annulus should be with a red dot. And I guess it's just nice to point out if you're not used to thinking about these things. For example, both this example and this example, if we instead we're just working in S3, of course, these would be unknots. But because we're working in a thickened annulus, these are like non-trivial knots in this thickened annulus. And this one would be an unlink if it was in S3 again, but it's non-trivial because we're restricting ourselves to thickened annulus. And I think there's a few places where annular links might not really appear. So like one example is if you really like thinking about satellites, annular links are kind of naturally what those patterns are, and studying annular links might tell you things about satellite operations. Fortunately, we won't see that much in this talk, but maybe something we'll see more is just that braid closures like this are really naturally annular links because when you're closing up, you're just kind of keeping track of the direction you've closed up in, and then you're naturally in a thickened annulus instead of in S3. And I don't know, braids are like quite nice objects to study and a great way to represent knots and links. So that's maybe another context in which you might see annular links here in some sort of natural way. That's nice to hear about annular links. So maybe I'll go on and tell you a bit about branch double covers and kind of relate it back to annular links. So just as I'm sure you're all familiar, if we had a link inside of S3, a very nice classical construction would be we could take the branch double cover of this link to build ourselves a 3-manifold by taking an honest double cover away from the link and using our link as the branch points. And this is, a great way to study links is like you have these nice tools you can use about 3-manifolds, and all of a sudden, if you want to prove something about a link, maybe you can prove something about the 3-manifold you've built and then like learn about the links that way. Or vice versa, like maybe you know a lot about your link and want to prove something about your 3-manifold. So this sort of correspondence has been used to great effect, right? And so what do we get if we instead are saying, actually, we have our link sitting inside of a thickened annulus, or alternatively, we have our link with a distinguished unknotted component in S3. This is going to give us a little bit more structure. Of course, we can still take a branch double cover over our link and get ourselves a 3-manifold. But now we actually have not just a 3-manifold, but inside of that 3-manifold, we have a nice 1-component or 2-component link by looking at the pre-image of this annular axis, this unknot. So now you can take, instead of just taking a link and building a 3-manifold, you can take your annular link and build a 3-manifold with a nice link inside of that 3-manifold. And you could maybe hope to play the same game of studying one of these objects by using stuff you know about the other one, either studying this annular link by studying links in 3-manifolds, or maybe vice versa.
When you do this, let's say from the S3 perspective,
yeah,
you're just doing the ordinary double branch
yeah,
cover.
just the ordinary double branch cover.
But in that case, shouldn't the pre-image of you be connected more or less by definition, construction, whatever you call it?
You mean like going from?
Yeah, right. Because at least the
maybe I can draw you an example,
sure,
and it would make you see why it might not be connected.
But you're just doing the double branched cover over L.
I'm just taking a double branch.
Oh,
yes.
Yes.
Yeah. So I'm not actually branching over you.
Okay. I think that clarifies.
That clarifies your question.
Yeah.
Okay. I think maybe it would have come up when I'm drawing it too, but I'm still going to draw an example because I think it likes to and highlight something nice, which is I told you one special type of annular link is a braid closure, and you might wonder, what if I know my link is a braid closure? Like, can I say anything special about this knot or link I've built in the 3-manifold? And I don't know, I can't draw that well in 3 dimensions, but I can draw you a nice picture in 2 dimensions. So if I wanted to think about a braid in 2 dimensions, I could think about it's just like marked points on a disk, and if I take this crossing it with S1, all of a sudden that's going to actually give me a braid inside of a thickened annulus. And in this picture, U really is this boundary here. And so if I take the double branch cover of this disk along the 4 marked points, in this case, I get this torus with 2 boundary components, where the involution is really rotate along this red axis. And I guess also this is maybe demonstrating that the pre-image of my unknot could be disconnected. It could be 2 components.
That depends on the linking number.
Exactly. It depends on if the linking number with U would be odd or even. Exactly. Here are my 4 branch points for this branch double cover, corresponding to the 4 points here. And so remember, to get my braid, I was actually taking this and then crossing it with S1. And when I guess with some monodromy, where I'm gluing back my disk to itself with some diffeomorphism of the disk with marked points. And so then if I wanted to actually build my 3-manifold, I can do the same thing. I can take this surface and move around in a circle. And just when I get back to where I started, I need some diffeomorphism for how I'm gluing my surface back to itself. And so this is a long-winded way of saying that if I started with a braid closure for L, this link I'm producing in a 3-manifold is actually a fibered link in that 3-manifold. That's nice. Like, lots of people like to study fibered links, and lots of people like to study braid closures. So like, it's there's tools you might be able to use to study one to study the other, or vice versa. And I guess I should say specifically, like, there's a nice relationship between the braid we're using and the fibered link coming from the Berman-Hilden correspondence, where the image of this mapping class group under the Berman-Hilden correspondence, which is very explicit, is actually the monodromy for the fibered link. So we understand the fibered link pretty well from understanding the braid. So then the third part of my title is Annular Khovanov Homology, and this is a tool I really like to think about and use to study annular lengths. And maybe I'll tell you, I won't give you a full definition, but I'll tell you something about what it is. So I should say Annular Khovanov Homology, it was maybe first introduced by Asai, Shizinski, and Sikora. Sometimes I give this talk with slides, and then what's nice is the names just come up when you like press a button, and you don't have to write out like everybody's name. But you know, then they don't get to hear me say this part in the slide talk. So I guess you all get to hear these nice comments instead. So you win some, you lose some. And maybe you can think about this as a category. It is a categorification of the Kaufman-Skein bracket, which is maybe just an annular version of the Jones polynomial. So it's much in the same way that Khovanov homology covers the Jones polynomial, this covers just the annular Jones polynomial. And it's defined in the same sort of way as Khovanov homology, where you're going to build yourself a cube of resolution. And the only difference is this is actually triply graded instead of Khovanov homology just being doubly graded. So the extra grading is recovering the fact that we're working with an annulus. And if you were looking at it, it's just really counting whether your resolutions are wrapping around the annulus or not. And so it has the regular homological and quantum gradings, and it also has this third grading that people often call the annular grading. And if that like didn't mean much to you, I've also just maybe written down some examples over here, so it might give you like a nice thing to latch onto, which is I'm just saying if it's going to take my annular link, and then for any triple of numbers, it's going to give me some vector space. So for this example here, I went ahead and actually computed it ahead of time. So over C, it gives you a two-dimensional vector space in this trigrading, a one-dimensional vector space in these other trigradings, and then it's 0 for everything else. And it's always going to be finite dimensional, like supported in finite lane gradings, finite dimensional in each of those gradings. And then, you know, for this one here, over F2, I computed it here. It's like one-dimensional in these 8 trigradings, and then 0-dimensional everywhere else. But you can always just think of it as something like this. It's going to take your diagram of a link, and it's going to give you like some vector spaces for every triple of numbers.
Is the intuition that the third coordinate is going to be bounded by 4 in absolute value because it goes around 4 times?
That is a great question. In fact, like yes, it's if I from the definition I gave, the half definition I gave you of like it's counting wrapping around this annulus, like that does mean because it goes around 4 times, this can't be higher than 4 as that third grading. Just like this one goes around twice, depending on how you count going around, and so it's bounded by absolute value of 2.
So is there a reason why you work with different coefficients in these examples?
Well, yes. So I think this one is maybe because I'll state a theorem about this where I needed to work over F2 to make one of the tools work. This one is because I was doing it by hand, and it's easier to compute over C because it has some extra structure. I could have just as easily done this over F2. I just wanted to use the extra structure so I didn't have to compute so much. But it's a good question. Yeah, that's why I should say, I guess this is also the same over C. So I guess another way of saying it is over Z. This one doesn't have any torsion.
Is it, when you're saying count how many times it goes around, are we computing winding number, but like the winding number of one of these resolutions?
Yeah, so I guess for each resolution, you would be looking at its winding number, or maybe if you don't want to take any resolutions, you could think about just the minimal intersection number with a disk that your annular axis bounds. Not counting any sort of sign. And you know, I mean, people like to study Khovanov homology, so it maybe seems natural that people would also like to study annular Khovanov homology. But I don't know, as a topologist, you might want to know, like, what is it telling you? Like, what does it mean? Instead of just saying, like, oh, I just get a bunch of vector spaces. Like, cool. So, like, what is it telling you? The good news is there is some things it tells you. Otherwise, it would kind of be sad if I brought this question up. So maybe the first result kind of pointing in this direction is a result due to a few people that it actually detects braid closures, so it can tell you just from looking at its annular Khovanov homology whether your annular link is a braid closure. And so I think the names here would maybe be, this is work of Grigsby and me in 2013, and then it's also expanded by work of Yi and Boyu Zhang. And their work is maybe in 2019. And how does it detect if you're a braid closure? It just says, look at the highest non-zero I also made a mistake when I was writing this down. But it says, look at the highest non-zero annular gradient and look at the dimension in that highest gradient. And it's not hard to check if you are a braid closure that that dimension would be 1. And then this detection results is saying that's actually an if and only if. And, you know, the highest non-zero annular, in that case, that will also tell you the braid index. So for example, here, the highest non-zero annular gradient is 4. So, and I just see that it's actually, there's only this one generator in gradient 4. So that tells me that this is a braid closure, which, I don't know, we can look at the picture and it's also a braid closure, but now we can just look at just this. And maybe going back to this example, how I've drawn it, it doesn't look like a braid closure. And there's maybe other ways you could prove it's not a braid closure, but, you know, a priori, maybe there's like some isotope you could do so that it becomes a braid closure. But you can look at its annular Khovanov homology, and its top annular gradient is 2, and it's actually 2-dimensional in that top gradient. So this ensures that it's not a closure of a braid.
So sorry for the question.
No, of course.
You've stated that result sounds very similar aesthetically to the way like Annular Khovanov detects fiber.
That was exactly what I was going to say next. Yeah,
okay.
Is if you do like an analogy to something like Annular homology, you should think of this as really like how Annular homology detects a fiber knot.
So is this only an analogy, or is there some like deeper connection?
There is some deeper connections, and like maybe we'll see it in a little bit, but this proof, I guess both proofs maybe use a connection in some way, though it's not as simple as just saying just because non-polar homology does, that also means that annular homology does. But that it is a great question, and definitely something you should have in mind when you see this. Is like it should be like how non-polar homology detects fiberness. There's some other things that we can say. So it also detects the trivial braid. And this is work of Grigsby and Baldwin. And so this just says, you know, if you have the same annular Khovanov homology as the trivial braid, then you actually were the trivial braid. And it's easy to compute the annular Khovanov homology of the trivial braid since it doesn't have any crossings. And, you know, I guess maybe I could say this also means annular Khovanov homology would give you a solution to the word problem in the braid group, but it's not as quick as like previously known solutions. Since then, there's maybe a few other results. So maybe another notable one is that it actually detects every two-braid closure and this is work of Grigsby, Anthony Licata, and Barely. And how do they show this? Well, we already know that it would tell us if we are a closure of a two-braid or not. And there aren't that many two-braids. It's just like how many times are you going to twist your strand? So they actually are able to compute the annular Khovanov homology of every two-braid. They're all different. So if you know you're a two-braid, you just like check against this list, and you're like, whichever one your annular Khovanov homology is the same as is whichever two-braid you have. So it's like a computational result in some way. And then Fraser and I were able to show that annular Khovanov homology detects the three braids, sigma 1, sigma 2, along with sigma 1, sigma 2 inverse. The four braid, sigma 1, sigma 2, sigma 3 that we see over there. And also the six braid, sigma 1, sigma 2, sigma 3, sigma 4, sigma 5. So this is I guess I should add dates here. So this one maybe is in 15, and then this was back in 2020. And then since then, there's been a few other things. So I guess maybe the most notable one is in our list, you might notice we go straight from a four braid to a six braid. And so people now are able to show that it also detects this five braid. And this is work of, just have to put the names in the right order. So this is work of Ethan Farber, Braden Reynoso, and Luya Wang, who are all currently grad students. So I think both Braden and Luya are also currently on the job market from BC and then UC Berkeley, respectively. I guess Ethan's applying for non-academic jobs, but it's maybe less relevant to tell you that. And I'm going to give you a sketch of a proof of what we did, and their proof follows like a similar strategy. And I think it should be maybe clear like what the extra cool work they do is. But if I give my sketch and it's not clear, like please let me know, and because I would love to point out like what they do. And then also since then. Fraser, along with his collaborator Subhankar Farday, are able to do the same sort of detection results for the 8 and 10 braids that follow the same pattern. I'm not going to write down the braid words.
So
yes.
I mean, these are things that you're able to deal with, but what do you expect, for instance, sigma 1 up to sigma n minus 1 in the in-braid group?
I would expect that that's also. I think the only reason it might not be detected is like kind of work outside of annular Khovanov homology, and would have to do with like results in non-polar homology. And I think when I give the sketch, maybe it will be clear like the exact result in non-polar homology. So like this question you're asking me is really boils down to a question of like, what do you think about non-polar homology detecting certain knots or links? Yeah, and I would be happy to point that out when we get closer to it. That becomes more obvious. I hope that's like a satisfying answer.
Yeah.
Yeah.
And is this like related to usual homology if you like if you just think about it in S3?
Oh yeah, sorry. I actually meant to say this and I didn't. So it's a great thing you asked this question. If you wanted to kind of forget you were in the NAS and instead work in S3, so on the polynomial level, you can just like set the annular variable equal to 0 and you'd recover the Jones polynomial. And then the right thing to do in this setting is you have a spectral sequence. So there's an algebraic relationship between annular quantum homology and quantum homology. All right, so I guess there's 3 things in my talk, and I told you about annular links, and we saw how they're maybe related to branch double covers. I told you about annular quantum homology. It's an invariant of annular links, so those are kind of connected, but I haven't really told you anything about how double branch covers and annular quantum homology might relate to each other. So that might be a nice thing to tell you too. So just to remember our setup, if we have our annular link, we were building ourselves this pair, which is a 3-manifold, where we're taking the branch double cover along L, together with this lift of the annular axis. And so if here we actually can look at the annular quantum homology of our link. And then if we have a 3-manifold with a knot inside of it, one thing you can do is you can look at the knot Floer homology of that knot or link inside of the 3-manifold. Knot Floer homology categorically represented polynomial introduced by Alibas and Szabo, defining it unfortunately outside of the scope of this talk. And these end up being related, again, by a spectral sequence. This maybe appears in work of Lawrence Roberts in 2007, and it's also in work of Grigsby and Verley in 2009. And if you are more familiar with the non-annular setting, you can maybe think about this as just, you should think about this as just an annular version of the Agra-Szabo spectral sequence from quantum homology to the Hegard-Floer homology of the branch double cover. And the construction works in much the same way. It's just the fact that you're working in an annulus and have this extra gradient ends up exactly corresponding to the Alexander gradient on the Knot-Floer homology setting. I mean, maybe you're already thinking this is cool because you like Knot-Floer homology, but if you don't inherently like Knot-Floer homology, like you might ask, like, well, why am I telling you this thing? Or like, why might you be excited to learn such a thing exists? There's kind of maybe a general moral reason to think that this might be a nice thing to know is that lots of topological applications of Khovanov homology come from finding a relationship with a Floer theory. So I think, in Jensen's talk yesterday, you mentioned that the fact that Khovanov homology detects the unknot is because Kronheimer and Mrfka show that it's related to an instanton Floer homology. And even other applications come via like an analogy with Floer homology, even if it isn't an exact spectral sequence. But maybe specifically, then you'd be like, well, why might it be helpful for these things I was telling you about? And so here's maybe where I'll focus in on our example that I've drawn over there of sigma 1, sigma 2, sigma 3. So if I look in the branch double cover of sigma 1, sigma 2, sigma 3, and I look at the lift of the great axis, this is actually the torus link T2 Floer. You shouldn't, like, this it shouldn't be, like, immediately obvious necessarily. Like, if you're not like, oh, yeah, of course, like, you shouldn't feel like you're missing something, but if you sat down, it would be very easy for you to check that this is true. And I should say maybe there's, like, some orientation issues, because I'm also suppressing some orientation issues here. And why might that be nice is because of this other theorem that Fraser and I proved, which is that if you take some knot, or I guess it's a link, sorry. If you take some link in S3 and it has the same knot floor homology as this torus link, then actually your link is the torus link. Or in another way of saying this would be that knot homology detects this torus link. Right, and I guess maybe to get to your question, like the question you were asking really will just boil down to if you think that knot homology detects the T2M torus knot. And so that's why when Ethan, Braden, and Louis proved that knot homology detected the torus knot T25, they also then proved annular Khovanov homology detected that 5 braid.
So to answer this question, for other braid closures, would you need to like reproduce their work, including all the train track machinery and so on?
So I think their work with all the train track machinery is, at least parts of it are special to wanting to detect something amongst genus 2 fiber knots. So maybe if you had some construction where you're building other genus 2 fiber knots in this way. But I think I'm not a complete expert, but I don't think that their proof strategy would necessarily work for like T27. At least like as it exists, because a lot of what they were doing was special to genus 2 fiber knots. Yeah.
With getting the what you said, that it went up with n equals 8 and 10. So you're looking at the torus links.
Yeah.
The 2.5, the 2.10 torus link, for instance.
Yeah. So I'm not actually totally familiar with all the techniques that Fraser and Subankar used, but like maybe more generally, I could say just like somehow the links are in some ways easier to deal with than the knots, because you have to have a bit more structure. It's like each component is an unknot. Like you can even act with like the linking number between them, or like if one is braided with respect to theirs. So maybe just as like an example for that, when Fraser and I wrote our paper, we also proved this for T26, even though Ethan and Braden and Luya hadn't proved this for T25 yet. And I think our proof for T26, it was easier for us to prove that than like all the work they had to do to prove it for T25. Yes, it's kind of strange, but somehow the links are easier than the knots.
One thing is the torsion norm is degenerate for T force.
Yeah.
It's toroidal.
Yeah, so I mean, I guess like building on that, like it's pretty easy to show link floor homology detects like T2N, and so you're really just trying to go from like knowing if link floor homology detects it to not floor homology detecting it. At least that's one strategy for the approach, but you can't do that for torus. So I think maybe I can just give you a sketch of the proof that that braid is detected by annular Khovanov homology. And like I said, kind of all the steps of it would work for, the same braid on, or the similar braid on like in the N braid group, except for, replace T2N by braid thing, and then the question of if not floor homology actually detects it. So say you have some link L, and you know that the annular Khovanov homology of L is actually the same as the annular Khovanov homology of sigma 1, sigma 2, sigma 3. It's closure. What are some things you can learn? Well, maybe remembering what I said about how annular Khovanov homology detects braid closures, we know that L is actually the closure of some 4 braid And using the relationship between annular Khovanov homology and Khovanov homology, we could also learn that L is an unknot in S3. And then using that spectral sequence and maybe doing a little bit of work, you could actually learn that the knot polar homology of the lift of the braid axis inside of the branch double cover of L, which is going to be S3 because L is an unknot, is actually the same as the knot polar homology of T24. And then that means that we know that the lift of the braid axis is actually equal to T24. You might be like, great, now we're done. We like know that this is the same as T24, but we actually need to know a little bit more because we know something kind of in a double branch cover. We want to go back to before we took our branch cover. There's maybe a few ways to do this in this case, but like this is one that works and that I like and also would work for any of these two or not. And maybe I'll say, so I told you earlier that, so maybe what's true is fiber links, if we fixed the way they fiber, are determined by their monodromy up to conjugation. So that means that, and we know that the monodromy is like related to the braid by its image under the Berman-Cohen correspondence. So that means the image of beta under this group homomorphism is actually conjugate to the image of sigma 1, sigma 2, sigma 3. And we really want to show that beta and sigma 1, sigma 2, sigma 3 are conjugate, because conjugate braids give you isotopic closures. That seems nice, except you can make up lots of group homomorphisms that send, even that are injective like this one, that send non-conjugate things to conjugate things. So you need to work a little bit harder. And a proposition that maybe Fraser and I write in our paper is that if you have a periodic braid, which we do in this case, sigma 1, sigma 2, sigma 3 is periodic, then this means that actually your braids have to be conjugate. And our proof uses the fractional Dane-Twist coefficient along with the fact that braids have unique nth roots if they exist, or kth roots if they exist. And I should say, it would be nice to know this in general. I asked some mapping class group people, and they seemed to believe it was true in general. Maybe told me they had like some sketch of an argument, but it sounds like it's never going to be something they actually write and publish. But they did have a sketch in the case of the periodic case, which they showed me I didn't understand, but I think maybe somebody who understood their thing better would think that it is also similar to what Fraser and I wrote down. And so I should say the people I was talking to were Marissa Loving and Dan Margulies. But it would be great, I think, if somebody just proves this and so that people can actually like A, know that it's true, and B, like cite it. Just in general, that for any braid, if your images are conjugate under the Berman-Hilden correspondence, then actually the braids are conjugate. At first, when I asked them, they didn't think it was true, but then somehow they convinced themselves that it was true.
What was the hypothesis of if you're a braid conjugate to?
So,
I'm sorry.
I guess if you have two braids and their images under this homomorphism are conjugate, then the braids are conjugate. Or, if you like thinking about it in terms of topology, if you have two braid closures and you do this construction of the branch double cover and get the same length for both, then actually the braid, you started with the same braid closure instead of two different ones.
So can I ask a question?
Yeah.
So a priori, I think we should only have the spectral sequence from the Annular Khovanov homology to pick up. homology. So how can you just derive an isomorphism there?
Oh yeah, that's a great question. It takes a little bit of work, but you can show that because this annular Khovanov homology is like simple in some way, that there's no differentials in the spectral sequence. It's already collapsed. But yeah, you're right. It's not obvious, and it's not true in general that just because you have the same annular Khovanov homologies, you have the same non-polar homologies. It takes some work there.
So can you just remind me then, what is the Berman-Hilden correspondence? Because
Yeah.
what about these like flights, these braid preserving flights, where you get two different braids that are not conjugate but have the isotopic closures?
That's something very different.
We can talk about something else.
Yeah. Joan Berman has done a lot of math, and so her name appears in a lot of things, which is cool, but also means maybe it's hard if you say her name, like to know which thing you're talking about. So this is something that she gives an injection from a braid group into a mapping class group of the surface you get by taking the double branch cover of punctured disk.
And I think the things you're describing, they're not isotopic in the thickened annulus, right? And
No.
correct me if I'm
Yeah.
wrong, Gage,
No,
you're
they're
just
not.
thinking of this setting where they are.
But when you said braid closure, I was thinking in S3, that you meant the braid closure in the annulus, thickened annulus.
I do mean the braid closure and the thickened annulus.
Gotcha.
Yeah, I mean,
Fair enough.
because I'm thinking about an annular link. Yes. Sorry if there was.
No, just all good.
Okay. This is like a part of the talk where I might switch gears a little bit for the last few minutes, 20 minutes, 15 minutes, somewhere in there. So I did want to say that in case people have more questions before I switch gears.
Okay, do one more question. So,
Yeah.
So there is a spectral sequence from Annular Khovanov homology to Higa Khovanov. This is like grading preserving for some of the gradings.
The annular grading corresponds up to like renormalizing exactly with the Alexander grading. Okay. So I think maybe after seeing something like this, you might be really excited because I don't know, things about Khovanov homology sometimes are hard to prove, but like lots of people study non-polar homology. We know a lot about it. We know a lot about how it interacts with topology. So you might be like, all right, if I have any question about annular Khovanov homology, I can turn it into a question about non-polar homology, and then use all those tools. I'm going to prove everything I want to prove. It's going to be like awesome. So here's a question you might want to know the answer to about annular Khovanov homology, and it's called the wrapping conjecture. And it's due to Hoste and Chizitsky. And what it says is that the highest non-zero annular grading is exactly the minimal intersection number with a meridional disk. And I guess like from Dave's question earlier, we maybe heard that this intersection number with the disk gives an upper bound on the highest non-zero annular grading, and that's very easy to check. So this conjecture is really asking if that upper bound is always exact. So like maybe in these two examples, we see the minimal intersection number with the disk here is 2, and our highest non-zero annular grading is 2. And here the minimal intersection number with the disk is 4, and our highest non-zero annular grading is 4. So in these examples, the conjecture is true. Also, maybe it wouldn't be an interesting conjecture. I gave you an example here at the start of the talk where the conjecture wasn't true, and just wrote it on the board right away. And again, like, because it might be helpful to think via analogy if you're more comfortable with non-polar homology, you should think about this as like the fact that the highest non-zero Alexander grading tells you the genus of your knot. Or, in link homology is like telling you a Thurston norm for embedded surfaces. And right, with that in mind, that analogy in mind, and the spectral sequence we've seen before, you might be like, all right, this is really great. Knot homology tells me about a Thurston norm with its Alexander grading. The annular grading corresponds to the Alexander grading under these spectral sequences. So I'm just going to use my favorite spectral sequence from an annular Khovanov homology to some sort of Floor theory and prove this thing. You could use the branch level cover like we've seen before. And I guess for experts, you could also maybe think about an annular instanton Floor theory or some annular version of knot homology as well. But you won't be missing anything if you only think about this branch level cover we've thought about before. So let's see if that works. So,
I have a dumb question.
oh yeah, of course.
This conjecture is from 1995.
Yes.
Annular Khovanov homology was
Yeah.
around 1995.
So they state their conjecture for the polynomial.
Wait, okay.
Which maybe since I wasn't talking about it, I just didn't want to. But that is a great question. Since I told you the Khovanov homology was introduced in 2004, and they weren't time travelers. Yeah. Right, and I guess maybe if you only ask about annular Khovanov homology, this is like a slightly weaker conjecture. But for the purposes of this talk, I think you can think of them as the same conjecture.
Okay.
So maybe let's look at these examples. So, here, this disk that intersects our Lincoln 4 points is the Thurston norm minimizing surface. Once you've defined your Thurston norm in the appropriate way to allow for these intersection points. And then here, in this example, the orange one isn't showing up well, so I'm going to pick a different color. This blue disk is also Thurston norm minimizing, but there's also another surface with the same Thurston norm in this picture, because you can also look at an embedded torus that I'll draw in purple here, where you just take your tube and you kind of follow the link around so that it never actually intersects. And these two would actually have the same Thurston norm. But again, this is an example where we could just use our spectral sequence to check that the conjecture is true, even though we already computed it. But then if we look at this example here, we have our disk, and it's going to intersect in 4 points. But if this disk actually no longer minimizes the Thurston norm in this example. There's actually this embedded torus, which does minimize the Thurston norm. And this torus never intersects with our link. And I think maybe seeing this, you could probably come up with an example where the minimal intersection number of the disk is 1 billion, but there still is an embedded torus that's keeping the Thurston norm very low. So this is actually not great news for our hope of using Floor homology to prove this conjecture, because the Floor theories are going to have their Alexander grading bounded, but that example you just came up with in your head, the conjecture says that the annular grading should be non-zero way, way up here. So that's a pretty big gap between what the Floor theories expect versus what the Floor theories see versus what the conjecture predicts. Maybe I should say here, just as a bit of history, this family of examples you thought of in your head was maybe first suggested by Matt Hedden and Stefan Verley shortly in 2010, shortly after Ellie Grigsby maybe first suggested this approach for proving the conjecture by using a Floor theory. And maybe these are the first examples that say it's not as easy as you might think. And I think there was new interest in this wrapping conjecture and connections with floor theory after work of Gage, where he related annular Khovanov homology with an annular instanton floor theory. And that was in 2019. And I actually remember maybe being in seminar dinners where people were asking, like, so did his work prove the wrapping conjecture before people kind of came up with these examples again? Kind of remembered them. And right, if you think this conjecture is false, this family you thought of would be like a great place to look for a counterexample, because, you know, maybe it's just that like a coincidence that the examples we thought of before, like the intersection number was really the same as the first norm. So we were just like kind of picking up on the fact that we have a Spectral sequence to a floor theory. But like if we come up with examples like this, where we see this big gap, like then maybe we could find a counterexample. That's kind of what was known for, like, it wasn't known if this family satisfied the conjecture.
Is the wrapping conjecture known to be true, like when the wrapping number is 2?
Oh, actually, that's a great question. You know, I think if it's true, you could probably make an argument that it's true just because you know that the not homology like can't just be supported in grading 0. So yeah, I think it would be true if for intersection number 2, but kind of because not homology like can't be trivial. I guess another way of saying that is maybe like if the intersection is numbers 2, any other surface you find couldn't have there's a norm less than the disk with 2 punctures. Just because the only way you're getting rid of punctures is by like adding genus, and one handle trades exactly for the 2 punctures. If once you've written down what it means to have a Thurston norm. And I guess I should have said it was known that the conjecture is true if you have a diagram that's called like plus or minus adequately wrapped, and they show that in their first paper. And it's also known to be true for string link closures, which a reference for is definitely like Ellie and Yini's paper that I cited, though Ellie seems to think it was known earlier, but I couldn't find a reference. And when I asked Shizitsky, he wasn't sure if there was an earlier reference. But
when you say string link closures, you just mean wrapping number 1. Is that right?
No, I mean like, and like, you know, any NN tangle where you, where when you flow from the top to the, like,
so it's
like an N string link closure. Like you could have
like no backtracking.
No backtracking, yeah. Maybe I'll just say that, like, instead of leaving you on a cliffhanger of if that family you thought of was a counterexample, I'll just say as a theorem, I showed that there are infinite families where the conjecture is true, even though the intersection number with the disk is much higher than the Thurston norm. So in these families, like the intersection number with the disk would be going to infinity even though the Thurston norm is bounded. And this really is maybe saying, like, there really is a possibility that annular Khovanov homology is seeing something about the topology here that we can't see with these floor theories. And yes, it does include, like, this family you thought of here. So the exact statement of, like, what this family looks like is a little bit technical. It's in my paper, so I'd be happy to talk about it if anyone was really interested, but I don't want to write it on the board. And maybe finish, I'll just say the key tool improving this is maybe extending the bats and seed link splitting spectral sequence to the annular setting, which isn't hard. I think other people knew you could do it because nobody had a good reason to write it down. And I knew you could do it for a while before writing it for this too. You just kind of take what they wrote and add the word annular in a few places, and then you're like, cool, I extended it to the annulus. And then maybe the proof idea would be, if I wanted to show it was true for this example here, I could use my link splitting spectral sequence. And maybe it's hard to see now that I've drawn on it a bunch, but if I forget about how these two components of my link link together, I just have two copies of this annular link here. And so you kind of get to reduce to a case where you can use a floor theory to tell you that the answer is true. And then it's just checking that your algebra also tells you that it was true where you started. But with that, I just wanted to thank you all for your time.